right, good afternoon, everyone. I hope you all are having a great day today. Beautiful weather outside. Certainly great opportunity for some stuff this weekend. But of course, that's not quite yet, so we've got class today. We'll be covering Chapter 9, which is Relational Model and Relational Algebra. Before we do that, I do want to make a couple quick announcements. First of all, I hope everyone's had a chance to get with their team for the group project in here. And at minimum, just kind of discuss the different topics that'll be covered on the project. So, there's about, I think, 9 or 10 different deliverables inside of the business report. Divvy those up. It's certainly a good thing to do. Assign some deadlines for your team so everyone stays on track with that. Certainly recommendations I'd have. However, ultimately, I'm only grading the final product. So, you can kind of decide with your team how you want to best pursue things. So certainly you have some flexibility there. Apart from that, certainly make sure that you submit the homework by Sunday at 11:59 p.m. If you submit it after that, it'll be marked late, and that's going to have at least a 25% penalty associated with it. So make sure you get that submitted. And then also, I think they're at a pause, or I'm not sure exactly what's going on with the construction. But I have been told that it should have ended on Wednesday. It doesn't look complete, but I also don't see them outside working. So hopefully there won't be any issues with that today. So right off the bat, we're going to be talking about relational model and relational algebra. So within this, you may be thinking, well, we've covered the relational model, and I would say that's absolutely correct. So if you have a good grasp on the relational model, the first part of the lecture will be a review. Having said that, I do think it's important to go through and just kind of make sure that everyone's on the same page. It's going to go a lot quicker than we would if we were explaining it for the first time, but just to make sure everyone has a good foundation on what the relational model is. So with that out of the way, what the whole purpose of the relational model is it's designed to kind of overcome some of the flaws and some of the problems that exist with previous modeling techniques. So you think prior to 1970, with the introduction of the relational database model, how were models made? Well, we didn't have relational databases, so they were made using procedural commands. That's very difficult to understand. If you were to look at one of those kind of earlier models, pre-1970, it wouldn't make a whole lot of sense. That's someone who would study a database could say that. So imagine explaining it to other business professionals. It can be very difficult. So the relational model addresses a lot of that. It makes it a lot simpler to understand. You have entities. You have relations between the entities. That's really all there is to it. So when we think about that, that's what this sort of addresses. Kind of looking at this at just a little bit more as to why some of the reasons for having the relational model exist. We don't have to use a command for each individual record that we do. So you think about this before, what you would do is instead of having maybe a select statement where you select all the records where something is whatever condition you apply. Maybe it's greater than 5, maybe it's greater than 20, whatever the case may be, you certainly have that flexibility. So with relational models, you don't have to apply some sort of a loop. You don't have to apply some sort of condition as you do with more procedural sorts of programming. So that's certainly a very important thing. And then you also think about, is it easy to write a SQL query? Overall, I would say it is. And when you're doing that, you can have people who aren't inside the database, it's not their job, they can certainly write database queries relatively easily. Or at minimum, they can give specifications, and it'll be a lot easier to accomplish, just have a quicker time overall. So when we talk about why some of the advantages are, beyond the problems with the existing models, there's also some advantages that relational modeling provides us. So we think about having our data be transportable. It's not tied into one specific system. We have a standardized format that we can take the data, move it between systems as needed. It's data independence is very beneficial. And without it, a lot of what we're doing wouldn't really be that meaningful. If we only can use the system for one specific data, we're not going to be able to get a whole lot of information from it. So certainly it provides that. Then, like I said, having the ERD, it's a very simple diagram to understand. And certainly when we consider that you can easily communicate what is inside of the data model and go from there, certainly. And then, of course, this is a lot easier not only for people to understand, but we think about who's actually managing the database. It's also easier for them to maintain. It's easier for them to understand. And that's going to serve to make it simpler for them to do their job, which will enhance their productivity overall. So there's three major concepts we're going to talk about with relational modeling. First being data structures, the second being integrity rules, and the third being operators. So when we think about a data structure, the biggest part we want to consider is what our data is. So we have this whole idea of being a domain. And a domain is kind of like saying, describing each individual variable. What is the variable? What values can it hold? So in this case, we can go ahead and we can say, will it have the same data type? Yes, it will. So within inside the domain of the variable, it's going to have the same data type. We wouldn't have a variable that sometimes is an integer and sometimes is a year and sometimes is a float, because that's not going to be a meaningful variable. That's going to be random. So not to say that some values won't be numeric, but we're going to treat them all the same way inside of the column. So that's what this is talking about. And we really define all of the rules for each individual column inside of here. So when we're talking about this, we want to be very clear that we're only talking about a single variable's domain. So let's say we have a variable for employee ID. We're not going to have an employee ID that sometimes is someone's name and other times is a number generated between 1 and 10,000, for example. So that's what we're talking about. We're talking about data structure and the domain. But beyond that, we don't just want to focus on an individual variable. We want to look at the bigger picture of things and see how these variables relate to each other and how they relate to other tables. So the whole idea is that we have relations. And the relations are saying that we have one entity that relates to another entity, or possibly entities. This doesn't have to be a one-to-one relationship. We can certainly have a relationship that involves more than two entities. So basically, what we have is we have two major classifications there that we want to focus on. So we have the cardinality, which is saying how many times does this relationship occur? In other words, you can think about this as being the number of rows. So if we had a student and a professor, we would say a professor has many students. Now, we could also say that a student probably has more than one professor. But if we're talking about a class, that's the way we would think about that. How many instances of that relationship occur? That's its cardinality. And then we have the degrees, which is saying how many of the columns are involved inside of that relationship. So it could be a case where there's more than one column inside of the relationship. And that's certainly something that we would want to model if that's the case. So the whole idea here is that we're going to model this effectively. We're going to be able to easily convey the information. And most importantly, we're going to be able to do so in a meaningful way. So let me talk about the structure of the data model. This is a very important concept, but it's also pretty straightforward. It's certainly stuff we've covered before. So to identify each instance of an entity, how do we do that? How can we uniquely identify each instance of an entity? So we use a primary key there. So if we have an entity, we're going to have a primary key that's going to allow us to uniquely identify each instance of that entity. Then, of course, we also have various things that could uniquely identify each instance. We refer to those as candidate keys. Now, a candidate key could be a primary key. Doesn't have to be, though. So if we have, let's say, a table, and we have inside of it country name, and we have inside of it country code, both of those are going to be unique. Both of those could uniquely identify the instances of the country, but only one of those is going to be the primary key. There's no reason to make a composite key when both could be the primary key. So they're both candidate keys. Both country name and country code in that instance would be candidate keys, but they're not necessarily both primary keys. So if we don't make it a primary key, then it's going to be the alternate key. And of course, lastly, if we have a foreign key, simply means that we're using it as it's a primary key in some other field, but then we're referencing it inside of another table. So, common example of that being, if you're taking a class, you're probably going to have some foreign key inside of your entity saying what class you're taking, something to that effect. So we've certainly done this before. Should be a review here. Then, of course, we have integrity rules. So basically what we're saying here is, how are we going to make sure that what we're doing is logical? That's the whole purpose behind integrity rules. So we have two major types of this. We have entity integrity and relational integrity. And then entity integrity, we're saying that each of the things inside of our entity, they follow the rules for that entity. So for example, we're going to make sure that if we have a column that is not null, that we set it to be not null. So primary keys are a great thing to do for this, but anything that you must have for it to exist, you need to make sure it's set as not null. And on top of this, we also want to make sure that we're able to uniquely identify each instance of the entity. If we can't do that, then the whole thing kind of falls apart, and we're going to run into a lot of issues. So we also want to make sure that all the relationships are logical and that they don't have any issues either. So if we have a foreign key, it needs to exist inside of whatever table it's referencing. That's certainly a very big one. That's all about referential integrity, making sure that the relationship is logical, making sure the relationship is able to fulfill the rules associated with it. So this is where we're going to get to some new information today. So this has been a review up to this point. Hopefully I didn't put anyone to sleep, but certainly this is where the information becomes new. So the whole idea here is we're going to look and see how can we actually manipulate the database to fulfill these different types of relational constraints. So we have a lot of different relations that we're going to talk about today, and we're going to talk about these from the context of relational algebra. Now, luckily for you all, this is not necessarily directly part of the exam. So I'm not going to have you be solving relational algebra problems, but it is important to understand, and certainly I could ask you a question about how do I do a project inside of SQL. Certainly something I could ask you. I could ask you, how would I make a join in SQL? That's certainly fair game, but I'm not going to ask you the relational algebra behind it. So let's just go through some of these. So we have the idea of restrict. And in restrict, what we're doing is we're taking a table or tables, and we're saying we only want to get certain rows of those table or tables. So we're going to apply some condition to that to only get things that meet this certain condition. So if you see here, we have A. We're only getting certain rows there. So that's what we'd be doing. Imagine we applied a condition like where x is greater than 2. Certainly something we can apply any condition we want. That's going to be done inside the where. So then we have project here. And in project, what we're doing is we're taking only certain columns inside of a table or tables. So how would we do this if we only wanted to get certain columns? So, I mean, that's certainly one way you could go about it. If we use the assignment operator, which is going to be the colon equals, we could do that. But basically what we're doing here is we're saying we're going to select each column we want in the order that we want them, and then just tell where you're selecting them from, any sort of join conditions you have. And then one of the really cool things about SQL is that we can use the select into logic. So if we say select these columns into, we can tell it where it's going to go. We can create a new table on the fly. I think that's pretty cool. Now, MySQL doesn't let us do it exactly like that. We have to do it in a different manner. But for most SQL implementations, we have the freedom to just say, select these columns into this place. So that's really all a project is. Sounds really complicated, but when we actually look and see what it is, it's not so difficult. So now this one may look a little bit intimidating. In a product, what we're doing is we're going to create a new sort of table using all the possible combinations of these two. So imagine we had two matrices, and this is all we're doing. We're just multiplying them together. So what we're doing is we're taking the V1, multiplying it by X1, and so forth, and ultimately we get a table that's going to be all the possible combinations. So basically, because we have three rows in this first column, we're going to have twice that because we have 2 rows in the second table, rather. So that's all we're doing here. You can imagine if we had more than a 2 by 3 and a 3 by 2, this would certainly get quite complicated. So, I definitely wouldn't ask you a question on the test to actually give the output of a project, because it'd be product rather, it'd be quite difficult. So a union though is going to be a lot simpler. When we think about a union, all we're doing is we're just going to create a new relation where we're seeing all the stuff that is inside all unique values basically. So here you can see we have x1, x2, x3, and then in the second table we have x2 and x4. So what we're doing when we make a union statement is we're actually just going to make a new table there, and we're going to get all the unique values from it basically. So if there's anything duplicated, we're not going to factor it in. We're just going to only have it in there once. So imagine a Venn diagram. We're going to get stuff from the A side. We're also going to get stuff from the B side. But if it's duplicated, we're only going to get it one time. Does that make sense? So you could do this several different ways. One of the easiest ways is just to use the union operator whenever you're doing a select statement. That's certainly one way. Another way you could, of course, get unique use the unique operator. You have two major ways to do that. And certainly, that's what this is for. This is pretty useful in a lot of cases. You want to get all the distinct values from two tables or more than two tables. You're not limited to only two tables. So it's pretty powerful. Intersections can be pretty similar, only in this case, you're only getting the things that repeat. So you think back to that Venn diagram, you're not getting it from both sides. You're getting it from the center where they intersect each other. So basically, with this, we have x2, x3, and then the second table still has the x2, x4. So what do those two things have in common? What do those two tables rather have in common? Exactly. So the intersection is going to be just what they have in common. So again, to do that inside of most SQL implementation, you can use the intersect operator. But MySQL doesn't recognize the intersect operator, so we have to use and exist. A little bit more complicated, but not too bad. Instead of using one operator, you have to use a couple in conjunction there. So now for difference, this is going to be something where we're going to take the difference and see what is not present inside of the second. So basically what we're seeing is we have the first, and then we have the second, and we're seeing what is inside the first table that's not inside the second table. So in this case, you can see both tables have x2. So in that case, when we take a minus b, we're not going to include x2 because we're looking and we're seeing what is only inside of a. So imagine we had a Venn diagram, we had a, we had b, and then we had the intersection. If it's in b and it's only in b, we're not having it. If it's in b and it's in a, we're not having it. We're only having the stuff that's only inside of a using the difference. So I wouldn't think of this as a difference as though you're taking 2 minus 1. Don't think of it that way. Think of it as though you're seeing what is only inside of a. Then we have a join. We've done a lot of joins. Hopefully this is a review. But basically what we're doing is we're saying, where can we form a join statement? So you can see here we have the example where what we're doing is we're doing an equal join. So we're going to join B where W equals Z. That's our condition that we're setting. So in this case, you can see W is equal to Z. We have WZ1 and WZ3, and then we don't seem to have WZ2 inside there. So whenever we make the equal join statement, the condition that we applied is only going to get V1 and V3 because these are the only two that are inside of the second table. So it's basically like a join statement, only we're using the equal join, and we're specifying that W must equal Z. So we can use any variable we want to there. We could call this variable X. We can call that variable Y. We've got lots of flexibility for what it's called. Don't get so caught up in saying that it must always be W and Z. That's really what I'm trying to say there. Whoops. Skipped about 3 or 4 slides there. So then we have the divide column. And what we're doing inside the divide column is we're taking a look at this and we're seeing, is there a value in the column X of A where we have the value of Y? So basically, what we're trying to see is how can we take that and see what is present, not necessarily inside of both tables, but what will be able to have a value inside of the first column is present inside of every value of the second column. So looking at this here, we can see that y1 and y2 occurs in both. And because of that, when we take the a divided by b, we're seeing we have the y. What is the x for that? So we have x1 is common between those two. Because it is common between those two, the a divided by b is going to get us the x1. So this one's a little bit trickier. I probably wouldn't throw this on an exam because, frankly, when would you use this? 10 points if you can think of a practical use of it in the next minute. So you're saying y would be price and x would be the clothing item? Give you that. I mean, there's not many uses of divide is what I'm trying to get across. So if you have a case where you would use it, here it is. But I'm not going to throw it on the exam because it's pretty complicated. You know, we want to make sure that everything's simple. So when we think about each of these 8 operators that I just showed you, each of these 8 different types of relational algebra operations, rather, there's really only 5 operators that we need to know. So the first would be restrict, the second being project, the third rather being product, the fourth being union, and then the last one being difference. And we'll talk about why that is. But the whole idea is that, you know, within this, a lot of these things like the join statements, you can do join statements several different ways. Whereas if using those 5 primary operators, you're only going to be able to use them in that particular way. So there's really no other way to do it. Now that's not entirely true because you're not limited to SQL. But for the purposes of this, just think of it in that way. Those are the 5 primary things. So we look at these and we say, how do we compare the relational algebra to the SQL statement? So again, if we wanted to restrict certain conditions, like I said, just you put it inside the where. So you have what you want, and then you specify that inside the where statement, whatever your condition may be. Same thing for a project, where you're only selecting certain columns. Right there inside the select statement, you're only going to get the columns that you actually need. When you're looking at the product, again, you know what you're doing. You're saying what information you want and where are you getting it from. You know, the union, of course, you just specify the union operator. You know, you're saying, what are we going to do? It's all done inside of these select statements. So pretty straightforward. Any questions about this? All right, feel free to stop me with any questions as we go. I'm certainly happy to address any. But then, you know, we want to talk about what a relational database truly means. You know, we kind of have an idea of it's a database that has relations between the tables, but it's important that we make sure that we fulfill the true definitions of it. You know, so COD's very particular in saying that if there's any flaw with the relations, it's not a relational database. Now, I'm not saying that's the standard we should be applied to, but we certainly want to make sure that we're avoiding all the problems with any sort of referential issues, any sort of integrity issues, and stuff like that. So that's really all this is saying here. We want to make sure that our data is logical and that it makes sense and that it's usable. So next, we have the COD's guidelines. And this originally said commandments. I did change that language just to make it, you know, just for personal reasons, I guess. But basically, these are the 12 rules that COD establishes for having relational models. So the first is saying the information rule. And what we're doing there is we're making sure that we're storing all the data that we need. We're not missing data. If we're missing data, then we don't really have a meaningful database. So we're putting all the data inside of the model, and it's going to be present, and we're able to manipulate it as needed. Then the second is saying we can access it, the guaranteed access rule. All this is really saying is that we can actually use these data that are present inside of the database. There's no sorts of restrictions on what we can access, what we can't access, not to be confused with each and every user having that. But at the end of the day, some user inside the database has full access to it. Then we have systematic treatment of null values. So that's saying that we're going to have some way that we kind of not only represent, but that we identify and we prevent any sort of values that are illogical from entering our database. So if we have a observation that says we have a employee who makes $5 billion a year, is that very likely? It's not likely that someone makes $5 billion a year, especially not in salary. Now you can make the argument, what if it's a CEO and we're a very large firm? Well, certainly, they're probably not making a $5 billion salary. They could be getting some heavy stock options, but the salary is probably under 100 million. There could be exceptions, but that's certainly pretty abnormal. Then we also have the active online catalog on the relational model, and that's something we're not going to cover too much. But basically, we're just saying there should be some sort of online catalog that's going to help us to describe what the relational model is, what it looks like, what the sorts of parameters are, all that sort of stuff. We're just saying that we can access the diagrams, basically. Then, of course, we have the fifth rule here, which is the comprehensive data sublanguage rule. And that's just saying that we're going to use some sort of language to actually manipulate data. In most cases, it's going to be SQL. So then we have the view updating rule, which is saying we have the ability to change the data as needed. So if we need to change the tables, we need to create new views, lots of different things, we have the ability to do so. Then, of course, we have the high-level insert, update, and delete. And basically, this is just saying that we can do each of these things. So we can insert new data. If we had a database and we created it in, let's say, 2010, has anything changed since 2010? Lots of things have changed since 2010. We go back and look. Maybe our customers have changed. Maybe some customers have quit being customers for us. Maybe we've gotten a lot of new customers. You can certainly imagine a case where if you could not do any sort of updating, deleting, your database is it's pretty pointless. So we definitely want to be able to use those insert, update, and delete statements. And of course, the physical data is independent. It's not tied down to one specific system. It's not tied down to only one way you can access it. This data is very portable. We can take it between systems, lots of different scripting languages we could use. We're not going to cover that too much in here, but the whole idea, we're not tying it down to one vendor's product. We're not tying it down to one platform. It's certainly going to be independent. Then beyond that, we have logical data independence. So I think about what that means. That's saying that anything that we have to the base table is not going to be affected by what the data itself is. So we want to make sure that we're going to be able to preserve that and to have some record of what was done to the data. Then we have integrity independence, and that's basically just saying that all the integrity constraints, they exist and that they're followed. So we don't want to have a case where we can just ignore the integrity constraints, because if we can, then what's the point of having the integrity constraints in the first place? There wouldn't be a very large point there. And then lastly, we have distribution, or not lastly, two more. So the 11th rule here, distribution independence. And this is basically just saying that the distributed data is not going to necessarily have a huge impact on any sort of applications that are using it. So what that means is that if we have a database and then we have various systems that we use, maybe like an ERP, something like that, we're not going to be affected if either of those systems changes. It's not going to affect the other systems. So this is one that's probably not going to be true in practice. A lot of times you make an update to something, a lot of things can break, especially in an enterprise environment. So we want to make sure that we're testing what we're doing to avoid that happening. Certainly you'd want to have test environments. You'd want to roll out the changes in test environments before, putting them on production. But, if you don't do that, you violated this rule here. And then lastly, we have the non-subversion rule. And it's just saying that we're going to only be able to update one thing at a time, because if we fail to do that, and we can update multiple records literally at once, then we could certainly run into issues where we're kind of skirting around some of the data integrity and data validation rules. Any questions about these guidelines? All right, well, I promise you won't have to regurgitate them on an exam, but just understand what they are and see how you could apply these guidelines to best practice. This is not necessarily new information here. This is certainly information that, as the course has progressed, we've gone through this, I'd say at a pretty good level. So, but then, beyond that, we're not quite done with Simicad's rule. He has rule 0. And rule 0 is simply saying that the relational database can manage all of the data that you have using the relational database. In other words, that's saying that the database can function. If we fail this, then we're saying it's not a relational database, and that's certainly something we don't want. So we want to make sure that the data model we have can be applied and that it can be a thing that we can easily use. If we can't, then we just wasted our time, basically. We don't want to do that. So that's going to be the rule 0. Just to kind of wrap up today, we went through a lot with the relational model. We talked about that. It's really, frankly, a review of kind of the first couple chapters, but we did cover the relational algebra, and that's a very important concept. Understanding the 8 major types of operations we can do, very important. Maybe divide's not as important as some of the others, but certainly there's some very important information there. And then lastly, we wrapped up talking about the various rules that Cod assigned. All right, any questions about today? All right, well, that's all I had, guys. I appreciate you all coming. I do encourage you all to continue working with your teams on the project and to submit the homework by Sunday at 11:59 p.m. Have a great weekend, everybody.